Hello, hello, my dear students. Yesterday we have dealt with subgroup. Which subset of G is a subgroup? Which subset is of G is not a subgroup? We will continue say with the same topic. Here, hello, my dear students. Just one minute. We have dealt. Uh, Yesterday we have dealt with if H and K are subgroups of group. Of course, one more result which we have proved, if G is a abelian group, H and K are subgroups of G, then HK is a subgroup which we have proved yesterday. And here, it is not given that whether this is a subgroup or not, of abelian or not. But when HK is going to be a subgroup, under that case, HK equal to KH ಇದ್ದಾಗ HK is a subgroup ಆಗುತ್ತಾ, ಇರಲಿಲ್ಲ ಅಂದ್ರೆ ಆಗೋದಿಲ್ಲ. ಅಥವಾ if one of them is a normal subgroup, then HK is a subgroup, which we will do it while considering the concept of normal subgroup soon. Okay, next period or day after tomorrow we can consider about that. Whether it is a subgroup or not, this result holds, that is, order of HK equal to order of H into order of K divided by order of H intersection K. This will hold whether HK is a subgroup or not. The proof for this you will find in topics in algebra by Ironhurstein and modern algebra by Surjit Singh and Qazi Jamiruddin, or Gallian. You can find the result here. I don't want to go for the proof of this one because it is a little bit lengthy also. From that, there is a corollary. The corollary says that H and K are the subgroups of G, then order of HK is greater than root of order of G, and order of K is also greater than root of order of G, then HK, H intersection K is not equal to identity. I mean, maybe considering more than one element. How to prove this one? Proof of a corollary. Now we can say HK is a subset of G, as whether it is, as I have told, it is a subgroup or not, but certainly it is a subset of G, and therefore order of J is greater than or equal to order of H into order of order of HK, or cardinality of HK. And by this result, what I am going to write down, this equal to order of H into order of K divided by order of H intersection K. H intersection K is a subgroup. We will prove in the next theorem here. Okay, and this is greater than, it is given that order of H is greater than root of order of G, and order of K is greater than root of order of G. I am replacing order of H and order of K by root of order of G and order of G only, divided by order of H intersection K, and that equal to order of root of this into root of this, same thing is going to be order of G divided by order of H intersection K. Now here you can see this is cancelled with this, and therefore what is that? 1 is greater than 1 by order of H intersection K, and this implies order of H intersection K is greater than 1. I mean, H intersection K is a subgroup, If H and K are subgroup, H intersection, we will prove this here only. Just wait for this. And this means order of H intersection K contains more than one element. I mean, H intersection K, H intersection K is not equal to identity only, means it contains uh, only what is that, more than one element, it shows. Now we have proved that. Okay, and also we can see order of H intersection K is greater than 1 also, and not equal to this. This is a very important result in connection with what is that, uh, connection with questions in IIT NET and IIT JAM and CSR NET, KSET and GATE, etc. Some questions will be asked on this result. Okay. Now next theorem we can see, if H and K are subgroups of J, then H intersection K is a subgroup of J. Now we can prove this one. A simple one. Let okay, let us see. E belonging to H because H is a subgroup. E belonging to K because K is a subgroup. This implies E belonging to H intersection K. That means H intersection K is not empty, non-empty subset of G. Now you can see we have to show H intersection K is a subgroup. It is sufficient to show that whenever A and B belonging to H intersection K, by the theorem, to show H intersection K is a subgroup, it is sufficient to show that AB inverse belonging to H intersection K. Now we will see whether it is true or not. Now, as we have considered H, A and B are in H, A belonging to H intersection H and A belonging to K, and also B belonging to H and B belonging to K, because both are in H intersection K. Okay, this implies A belonging to what is that, H, and one more step we can write down A belonging to K, and H and K are subgroup, therefore B inverse belonging to H and B inverse belonging to K, because H and K are subgroups. By the theorem which you have already done, two what is that, two-step proof. Here you can say A belonging to H intersection K by this. Okay, by this B inverse belonging to H intersection K, and therefore AB inverse belonging to H intersection K, and hence H intersection K is a subgroup of G. Okay, now we can see, 1 minute, only 1 minute. Yeah. Now, if H and K are subgroups of G, intersection of those two subgroups is again a subgroup. In other words, any two subgroups whose intersection is always a subgroup. It is a theorem uh, proved in theorem 6 now, just now we have proved. Okay. Now you can see one more example of a subgroup. Okay. Example 12, G equal to Z plus means set of integers under the operation of addition. It is a group. Okay. And Hn, now I am going to define Na such that A belonging to Z. Okay. All multiple of N, H, then Hn is a subgroup. Prove this one. Okay. Instead of proving this one, of course, I would like to take some particular example when n is equal to 2, Hn equal to 2 into A such that A belonging to Z. Okay, what is this exactly? The all multiple of 2, all multiple of 2, all multiple of integers, multiple of 2. This can be written as 0, 2, 4, 6, etc. and -2, -4, -6, etc. Is it not? It is a set of all even integer. This can be written as E, or I can write down 2 into Z. Means multiply all elements of Z by 2. Okay. It is a clearly a subgroup. It is a clearly subgroup because identity is there for addition of any two numbers is again a number because addition of two even number is again even number and hence it is so. And inverse for every positive integer, positive one number, there is a negative one number and hence it is a subgroup. Similarly, in general, we can prove this one. Let me consider for the sake of some result, I am going to uh, take one more example, K. This let me call it a 2Z. What is a 3Z? 3Z. I would like to call it as a H, okay? And 3Z, I would like to call it as a K, okay? 3Z equal to 0, all multiple of 3, 3, 6, 9, 12, so on so forth. -3, -6, -9, -12, so on so forth. This is also a subgroup because 0 is the identity here, as in the case of K, and for every multiple of 3, positive multiple of 3, there is a negative multiple of 3, and addition of any two multiple of 3, again it is going to be multiple of 3, okay? It is also subgroup. Now, what about from the previous result, what we have proved, if H and K are subgroup, H intersection K is also subgroup. Here, is H intersection K, by that result, is a subgroup. What is that group? Or I can write down this. Means H intersection K. It is a set of all integers which are multiple of 2 as well as multiple of 3. Okay, that is H intersection K equal to 2Z intersection 3Z. What are those elements? Can you imagine? Solve ವಿಚಾರ ಮಾಡ್ರಪ್ಪ. What are those elements? All elements which are multiple of 2 and also which are multiple of 3 belonging to this set. Okay, how I can write down? Common element. 2 is not belonging to 3z. Okay, 4 is not belonging to 2z, but 6 is belonging to this one. 0 also belonging to this one because 0 is in both the sets. Next element, what is that? Which is divisible by 2 and also 3. 2 and also 3. Here 2 and 3. You can take the LCM. 2, 1, 3, 3, 1, 1. So LCM is 6. Means here 2z intersection 3z is all the multiples of 6. Okay. Minus 6, minus 12, minus 18, so on so forth. This is also exactly, what is that? 6z. Okay, 2z, and it is a subgroup. Okay, alright, subgroup. Now, what about H union K? I mean, 2z union 3z. What is this set? Here, intersection is 6z. Now, I would means all elements of 2z and all elements of 3z. Now, 0, okay, and 2. And okay, I would like to write down 4, 6, so on so forth, and also minus 2, minus 4, minus 6, so on so forth. This is a multiple of what is that? 2z and 3z. 0 is already there. 3, sorry, I can write down here like this: 3, 6, etc., and minus 3, minus 6, etc. Or I would like to write down in one symbol, one node: 0, 2, 3, 4, 6, 6, okay, etc. All multiple: minus 2, minus 3, minus 4, minus 6, and minus 9, etc., minus 8, sorry, plus 8 and 9, so on and so forth. Now, is it a subgroup? Now, think of H union K. This is a subgroup. Though H and K are, what is that? Subgroups. But H union K need not be a subgroup because here 2 and 3 belonging to H union K, but 2 plus 3, addition is the operation, is equal to 5, does not belong to H union K. Okay, followed my point. H intersection H and K are subgroups, then H intersection K is always a subgroup. But union of two subgroups need not be subgroup. This is an example where when union is going to be subgroup, only when either H is a subset of K or K is a subset of H. One of them holds good, then H union K is a subgroup. Okay, and next we'll go to next example. Now here, very interesting subgroups. Example of a subgroup. S is any set with let us say S equal to x0, x1, x2, etc., xn minus 1, n elements. Okay, yes. And AS is set of all permutation F such that F is a permutation on S. Permutation means 1 1 and on to mapping. Set of all 1 1 and on to mapping, which we have already discussed about this subgroup. Usually we are going to write down Sn. Sn is a group that's called symmetric group. We will deal with this group in detail in future, okay? Because that is also a very important group where the questions from NET, IIT JAM, GATE, etc. we are encountering that, okay? All right. Here H is Hx naught. X naught is an element of S is equal to set of all phi, I can write down this set of all phi belonging to AS such that phi of x naught equal to x naught only. Okay. Now, is it a subgroup? Question is it a subgroup? Question. Okay. Now observe whether it is a non-empty or not. Now, E belonging to I belonging to identity mapping belonging to AS and I of x naught equal to x naught only in case of identity matrix, identity function, every element is mapped onto itself and therefore I belonging to Hx naught. Okay, and this implies Hx naught is not empty. Okay, next we have to show that inverse element. Let me consider okay, product of two mapping. Okay. Here, let phi and psi belonging to Hx naught means that phi of x naught equal to x naught only and psi of x naught is also x naught. Okay. Now, what about product of this mapping? Phi into psi. What is that? X naught. By the definition of the product of mapping, phi of psi of x naught. Okay. By the definition of psi here equal to phi of x naught. Again, by the definition of phi is equal to x naught. And therefore, phi psi belonging to product of two such mappings belonging to Hx naught. Okay. Next, let me consider the inverse element phi belonging to Hx naught. Whether this is property number 1, phi and psi belonging to Hx naught. One is a non-empty, second one closure property, third one we have to check whether inverse element exists or not. Okay, this implies phi of x naught equal to x naught only, and this implies inverse of phi of x naught equal to phi inverse of x naught, because multiplying on the left by phi inverse, and this equal to identity of matrix phi into phi inverse equal to identity, that is phi inverse x naught. Identity mapping always mapped onto x naught, that is phi inverse x naught, and hence for every phi belonging to Hx naught, phi inverse also belonging to Hx naught. That is the what is that? Two condition theorem. H is a non-empty, Hx is non-empty, and AB belonging to H, then A into B belonging to H. And the third one, For every A, there exists inverse element. All the conditions in the theorem are satisfied, and therefore Hx naught is a subgroup. Okay, therefore it is given as an exercise in Hurstin book. Okay, but solution is not given. I am giving solution. I have given already a solution, and similar is a subgroup of AS. Okay, or SN. Okay. Now next one K, or I can write down, sorry, Hx1. Let x naught is not equal to 1, x1. Okay, here what is that? All those permutations which are where x naught is a fixed, phi of x naught equal to phi x naught only here, and h of x1 is equal to set of all psi I can write down, psi belonging to AS. Okay, such that psi of x1 equal to x1 only. Here x1 is fixed. Not necessarily you can take any other element which is not equal to x naught, and that also a subgroup, so that h of x1 is a subgroup. A similar way which I have proved hx naught is a subgroup. Okay. In the Hurstin book, he has asked, what about hx naught intersection h x1? Is it a subgroup? Yes, of course, hx naught is a subgroup, and hence hx1 is a subgroup. Then intersection is always a subgroup. What are the elements of this hx naught and hx1? This is set of all psi or phi belonging to AS, such that psi of x naught equal to x naught and psi of x1 equal to x1. Means here two elements are fixed by the permutation. Now in particular let me take S3. Okay, S3. S3 contains I, F, G, H, and what is that? Phi, psi. Okay, these are the elements. F equal to, as I have told, 1, 2, 3, 1, 3, 2. Here 1 is a fixed. Okay, and here 2 is a fixed. Here 3 is a fixed. Only in this case, H1 or HF, H1 you can say, set of all F, such that F of 1 equal to 1. Okay, this is a subgroup because this contains I and F only. Okay, H of 1 again, this is also G, I and G. There also H of G is equal to 2, 2 is a fixed, and H3, 3 is a fixed, I and H. ಓಕೆ H4 H3 ಆಯಿತು. ಆಮೇಲೆ ಇವು ಮೂರೇ ಸಬ್ಗ್ರೂಪ್ಸ್ ಇಲ್ಲೇ, ಹೌದಾ? ಆಮೇಲೆ ಇನ್ನೊಂದು 3 ಎಲಿಮೆಂಟ್ ಸಬ್ಗ್ರೂಪ್, ದಟ್ ಈಸ್ I, phi, psi. That is also a subgroup. Okay. Next example. Okay. This is a very interesting example. Now observe. We have already uh, seen that G of GL of NF is a general linear group. General linear group. This is set of all matrices n cross n such that determinant of determinant I would like to write down this is not equal to 0. This is a subgroup and hence it is called a linear subgroup over the field F. Instead of that, I am going to take a particular case n is equal to 2 and F is equal to R. G is GL, general linear group, 2R is equal to what is that? 2R means A, B, C, D such that determinant of this is not 0. I mean AD minus BC is not equal to 0. This is a subgroup. It is a group of real number, general linear group of a real number, and this one elements of this are of the form. Okay. Now observe in this group, you know, AB belonging A, B, C, D is a 2 cross 2 matrix. What is the inverse of this? Please be remember this. D divided by AD minus BC minus B divided by AD minus BC and minus C divided by AD minus BC and D divided A divided by AD minus BC. Because AD minus BC is not equal to 0, instead of this you can write down D divided by determinant of A and minus B divided by determinant of A and minus C divided by determinant of A and A divided by determinant of A. This is the inverse of the matrix A, B, C, D. Okay, this is the inverse of this. Okay, keeping this in mind, consider the set H is equal to set of all a square matrix of the type AD 0D and such that AD is not equal to 0. Here AD is not 0 into D. AD minus 0 is not equal to 0 means AD equal to 0. This is a subset of G or G equal to L GL to R subset, only subset. But whether it is a subgroup or not, we have to check that with the properties of the subgroup. Properties of the subgroup. Three conditions. Whether first it is a non-empty, the second one a product of two matrices is again a matrix of that form only, and third one inverse. Third one is inverse. What is that inverse? Okay, now you can see clearly 1001 belonging to H identity matrix. Is it not? Because 1 into 1 is 1 only, not equal to 0, and therefore H is a non-empty subset of G. Okay. The second one, this is 1. Second one, Product of two matrices is again a product of this matrix only. Let A1 D, sorry, A1 B, this is B, A1 B1 0 D1, one element, and A2 B2 0 D2 belonging to H, let us say. Their product, therefore, their product, or I can say A, this is equal to A and this is equal to B. Okay, AB equal to A1 B1 0 D1 into A2 B2 0 D2. Product ಏನಾಗುತ್ತೆ ನೋಡ್ರಪ್ಪ, first row with the first column of the second matrix. First row A1 A2 ಹೌದಾ, and B1 0 plus 0. Okay, and first row with the second column A1 B2 A1 B2 B1 D2. Okay, next second row with the first column 0 plus 0. Okay, and next second row with the second column 0 plus D1 into D2. Now you can see here A1 A2, next A1 B2 plus B1 D2 0 and D1 D2. Okay, now observe, this is of this form. A is replace it by A, this replace it by B, this replace it by D. So the form is same and therefore belonging to H. A product of any two such matrix is the same form of the matrix what we have got. Okay, now what is the inverse of this? And now we can say, therefore, second property, if AB belonging to H, okay, A into B belonging to H. Okay, now next looking at the inverse element. Okay, what might be the inverse of A? Now A B 0 D, inverse of this equal to, recall that definition of this one, A B C D, inverse is what is that, D divided by matrix of A and minus B divided by matrix of A and minus C divided by matrix of A. A means AD minus BC and A divided by matrix of A, which you have already discussed just now. Okay, here inverse of this AD is not equal to 0. Here determinant of, or I can say determinant if A equal to A B 0 D. Okay, let me say determinant of A equal to AD, which is not equal to 0. Just observe, not equal to 0. Okay, and therefore this is D divided by matrix of A and minus B by AD, or I can write down AD only, and this is AD and next minus C by AD determinant and A by AD. Okay. Now this I can write down simply 1 by A because DD cancels, and minus B by AD. Okay. And here minus C by AD. And this I can write down, this A is cancelled 1 by D. This is the inverse of that. Okay, you can check that, you can verify AB 0D into 1 by A minus B by AD and minus C by AD and 1 by D is equal to 0, 1, 0, 0, 1 identity matrix, and hence a third property also pursued. For every A belonging to H, A inverse belonging to H, and therefore this is a subgroup. Subgroup of what? Subgroup of general linear group of over uh, 2 cross 2 matrices. 2 cross 2 matrices. Okay. And one more example I would like to give here. Of course, whether I have mentioned or not, okay, not mentioned. Here only I would like to give. Now, H equal to shortfall matrices of the form 1, B, 0, 0, 1, such that B belonging to R or Z I would like to write down. B belonging to Z. And this is of the form H2F. Heisenberg group, as I have already told, upper triangular matrix 1, B, 0, 1 is an upper triangular matrix. This is just upper triangular matrix. Okay. This is a group which you have already proved. Heisenberg group is a group. Okay. Here, identity is 101 identity, and hence non-empty, and this 1B01 B1 I let me take, and 1B201 is again a matrix. Just observe a matrix 1 into 1 B1 into 0 1 only, and next first row with the second column B2 into 1 B1. Next second row with the first column 0, second row with the first one 1 only. Now B1 and B2 belonging to Z, and therefore B2 plus B1 also belonging to Z. What about the inverse of 1B01? What is the inverse? I will leave it as an exercise. You check it. 1 minus B01. Or I can write down 1B01 into 1 minus B01 equal to 1001 identity matrix. You can check it out. Here it is a subgroup of Heisenberg group of 2 cross 2 matrices over integers or over real numbers. Okay. All right. Now observe here. Give non-zero complex numbers with multiplication as a binary operation. G equal to set of all a plus ib. Non-zero complex number means a is not equal to 0, b is not equal to 0. So 1 is the identity, of course. 1 plus I into 0 we can write down. And h equal to a subset. Set of all a plus ib such that a square plus b square equal to 1. A square plus. Show that H is a subgroup. H is a subgroup. Okay, now we can say uh, 1 belonging to this. How you know? We can write down 1 plus I0. Okay, this implies 1 square plus 0 square is 1 only. Okay, and therefore 1 belonging to H, and therefore this is the first property, non-empty set. Therefore H is non-empty subset of set of complex number. Now we can see inverse, and this inverse also we have seen that inverse of a plus ib equal to minus a divided by a square plus b square plus ib minus ib divided by a square plus b square, that is inverse. Okay, let it be. Now a plus ib belonging to h and c plus id belonging to h. Now whether a plus c ac plus I into bd belonging to h or not, we have to check it. Now consider from this a square plus b square is equal to 1. Call this is a 1. And from this c square plus d square is equal to 1 because they are element of h. Okay, whenever they are element of there, then square of the real part and plus the square of the imaginary part is 1. Now we can consider, uh, you know, a plus ib under multiplication, c plus id equal to binary operation of the multiplication over the complex numbers. What is that? AC minus BD plus I into AD plus BC. This is the way we have defined a multiplication over the set of complex number, and hence we have proved that it is a group. Okay, already we have already dealt with. Okay, now with this, now consider AD, the AC minus BD whole square plus AD plus BC whole square. Why I have considered? No, this is A, this is a B. A square plus B square is equal to 1 ಅಂತ ತೋರಿಸ್ಬೇಕು. ಅಂದ್ರೆ this square and the real part, square of the real part and plus square of the imaginary part is also 1 ಅಂತ ಪ್ರೂವ್ ಮಾಡಬೇಕು. ಹೌದಾ? ಈಗ ನಾನು ಏನು ಮಾಡ್ತೀನಿ, ಈಕ್ವಲ್ ಟು ಇದನ್ನ ಸ್ಕ್ವೇರ್ ಮಾಡ್ರಿ, a square c square minus 2abcd plus b square d square. Okay, next plus square of this part, a square d square plus 2abcd plus b square c square. Okay, and this is getting cancelled with this one. Now I will adjust the term. First I will like to take a square c square Then I would like to take this one plus a square d square plus b square d square. This I have taken. Next b square c square. Okay, now that equal to, here I would like to take this a square outside, a square into c square plus d square. Okay, plus b square I would like to take, b square equal to c square plus d square, and that equal to a square into 1 plus b square into 1. Why? This is by 2. Here c square plus d square is equal to 1. Wherever c square plus d square, I substitute that one, a square plus b square, and by 1 again is equal to 1 by 1. Okay, and therefore this product of two complex number is a complex number, and we can find out the what is that? Find out the inverse of that, and hence this is a subgroup. This is a subgroup of G. Okay. Let me stop here. Next class, I mean tomorrow class, we will see the center of a group. What is the center of group? Just I will define this one. G is a group. ZG denote a center of a group. I mean set of all X such that X belonging to G such that XY equal to YX, where Y for all Y belonging to G, or in other words, all those elements which are commuting with every element of G, all those elements which are commuting with every element of G. For example, okay, let me do it tomorrow, okay, in detail with many example. I would like to give those example. Okay, let me stop here. Okay, this is a very interesting subgroup of G. Again, this is a subgroup of G. First, we will prove that it is a subgroup of G and find center of many particular groups. Okay, those are very important in the point of view of examination. Thank you, one and all. Let me stop.